All right, now I want to continue with the second half of section 12.1. I want to finish that off. There's not a lot of theory left, so I want to talk about it just ever so briefly because it brings in another formula, and then we will do that practice question. I'm just trying to find my notes. Sorry. Okay. Yep. All right. So at the bottom of page 580, there is the beginning of what we call gravity and Kepler's law. So when we left off in the theory, we were talking about Newton. And the fact that Newton had come up with this formula we were dealing with, which was force of gravity is G m1 times m2 over r squared. But he actually didn't know what G was. That actually wasn't found until about 70 years after he died. That value, he didn't know what it was. However, this formula still came in handy because what he did was he compared it with Kepler's laws, and he basically sort of combined them to come up with a new statement. So Newton had already shown that the inverse square relationship between gravitational force and the distance between the masses was supported by Kepler's first laws, that planets followed elliptical paths. So he said this whole thing, the fact that the two masses are proportional to one another and inversely proportional to how far apart they are, that's actually supported by the idea that Kepler said planets moved in an elliptical pattern, because if you follow this formula, it makes the planets go in elliptical patterns. So the math and Kepler's conjecture about the shape of the orbital paths actually made sense together. Kepler's second law, which said that it sweeps out equal arcs in equal sector areas in equal amounts of time, which actually meant that when the planets were closer to the sun, they moved faster, and when they were further away from the sun, they moved slower. Again, that was supported when you did the math. And then finally, Kepler's third law was really a statement, a math statement. And that math statement said that if you took the radius and cubed it and divided by the period squared, and the period is how long it takes it to go in its elliptical path around the sun, you would always get a constant. And it was a constant for anything. He didn't know what that constant was, but he knew it did it. And so what they did was they took this idea that r cubed over period squared is equal to some constant, and they took the idea that force of gravity is equal to G times m1 times m2 over r squared. They actually took those two ideas and the idea of centripetal acceleration, so they brought that in, and centripetal force, mv squared over r, they brought all of that together and they came up with this new formula. Again, there is the derivation of that formula on page 583. If you are a person who likes to see where did this formula come from, they write out each individual step on page 583. Again, I can do it. I've done it, but I don't want to confuse you, especially via video. But when they combined the idea of centripetal force, the idea of Kepler's third law, and the idea of universal gravitation, and they combined it all together, they actually got this formula that helped them figure out what this constant is. They said this constant actually works out to be G times the mass of the sun over 4 pi squared. And the pi is the thing that is squared. There's not brackets around that, so the pi is the thing that is squared, not the 4. And again, they came up with that by combining several different formulas together and mixing them all together. So now, instead of Kepler's third law saying r cubed over period squared is equal to some constant, they said it's equal to the universal gravitational constant times the mass of the sun over 4 pi squared. Now, we're going to use this formula to talk about some calculations that you can do with that. But before we get there, it says all of Kepler's laws developed prior to the time when Newton did his work. So Kepler developed his laws before Newton did his work. But they all support Newton's law of gravitation, of universal gravitation. In other words, Newton's law about universal gravitation and Kepler's law, they supported one another. The math worked out using both of them, all right? One did not negate the other one. In fact, they helped each other. Kepler had focused only on the sun and the planets. But remember, what Newton did differently was that he applied his laws to all types of orbital motion. So he didn't just say the planets around the sun, but he said the moon moves around the earth in the same way. And what we know today is that when we put a satellite out in orbit, it follows these rules too. The International Space Station follows this rule. And it's actually really important because when they put a satellite in orbit, they need to know precisely where to put it so that it does what they want it to do. And orbits are always decaying, by the way. They're always, because there is gravity, they're always going to slowly decay. When they do that, eventually the satellites actually fall back to Earth, eventually. And so scientists have to do all this math because they have to know exactly how long is that satellite going to last up there before it does fall to the Earth. They have to make sure that when it does fall, it doesn't fall over like New York City, because most times when those satellites fall, it breaks apart and the pieces all burn up on re-entry. But sometimes not all of the pieces do break up on re-entry. So they want to make sure that these pieces of satellite or whatever are not going to fall onto a metropolis. So there's actually extensive math to take place. There is one more piece of information, and it actually was a question that someone asked me, and it said, have you ever looked at the tables that contain the data for the mass of the sun and the mass of the planets and wondered, how do we know? How do we know what the mass of the sun is? Who went out with a big scale and weighed it? How did we figure this out? Actually, that was actually figured out by a guy named Henry Cavendish. Henry Cavendish lived from 1731 to 1810. Interesting fun fact, he was very, very reclusive, didn't like to go out in public, didn't want to publish his work, didn't really want any attention, but was super, super smart. Did all kinds of experiments, made all kinds of notes, but didn't really do anything with them. As a result, there's a lot of things that we know today that actually are attributed to other scientists, but Cavendish figured it out first. And when they got a hold of his notes, they published it under their name and they got credit, but Cavendish actually did it. That's in the little history link on page 584. It says he was rarely seen in public other than at scientific meetings. His work was meticulous, but he didn't really publish it because he didn't want the attention. So after his death, other scientists discovered his notebooks and they published his results. And Cavendish had performed the same experiments and obtained the same results for some experiments that were later done by Coulomb, Faraday, and Ohm, who all worked with the idea of magnetism and electricity and those types of things and are very, very famous in their fields. But they got credit for the work, but they were actually working off of Cavendish's notes. So one of the things that Cavendish did, and I can't really explain this because I don't totally understand it myself, but he really wanted to figure out what this constant G was. He's the one responsible for figuring it out. Remember I said they didn't figure out what G was until about 70 years after Newton died? Well, Cavendish was the one who figured it out. And what he did was he created something called a torsion balance, and there's a picture of it on page 584, and I've even tried to find videos on it. I have not found one that explains it in a way that is in any way simple or understandable because it's so complicated. But he used the mathematical relationship in Kepler's third law to calculate the mass of the sun. So Cavendish designed what's called a torsion balance, and again there's a picture of it, and it allowed him to measure G. A torsion balance can measure extremely small amounts of rotation of a wire. So first, the torsion balance has to be calibrated to determine the amount of force that causes the wire to twist by a specific amount. So how much force do I have to do to twist this wire this much? Then large spheres are positioned so that the bar supporting them is perpendicular to the rod supporting the small spheres. And again, you can see a picture of this, but it's really complicated to me. And by measuring this, in this position, the large spheres are exerting equal gravitational attractive forces on each small sphere. The system is in equilibrium and the scale can be set to 0. The large spheres are then moved close to the small spheres, and the amount of twisting in the wire is determined. From the amount of twisting and the calibration, the mutual attractive force between the large and the small spheres is calculated. Using his torsion balance, Cavendish calculated the value of G to be 6.75 times 10 to the negative 11th. Now remember, today with all our sophisticated instruments, we know it's 6.67 times 10 to the negative 11th, but notice how close he got just using this like pieces of wire that he hung from a ceiling somewhere. The best known figure today is 6.67259 times 10 to the negative 11th. He was within 1% of the actual value that we know today. And he used this and this formula that we have here now to calculate the mass of the sun, which then you could use to figure out the mass of the other planets. I'm actually going to stop the video here so that I can go eat my supper. Then I will come back and do the math. All right, so I will be back in what for you is no time at all.